Hi everyone, so today we're solving the physics periodic quizzes for week 4, and this I'm gonna be doing chapter 8. Tariq is probably gonna be doing chapter 7. So let's start. The first question is this one. It's asking the internal energy of a system. By the way, this is the 8.1 to 8.3 quiz. The internal energy of a system can be thought of as the sum of the random kinetic energy, the intermolecular potential energy, and the chemical potential energy of its particles. This question, just memorize it. It's defining the internal energy of a system. It's a definition. For anything that says define, just memorize it because they can't change it later on in the exam. They can't change the way they give you the question though. Depending on the context, the heat energy can refer to a random thermal energy, internal energy, and radiant energy. For these, you could put them in any order other than this one, because here they gave you the word random, and it's not any thermal energy, it has to be random thermal energy. So just be careful if they give you a word like this to put thermal after it and not put anything else. But again, memorize it. Okay, so for this question, it's asking you which interactions happen with or without energy transfer. So let's start. A spring being compressed. So why does this happen with energy exchange? Because a string, it starts off like it's long, it's uncompressed, so it's big, so it's standing. But when you compress it, it becomes something like small and like it becomes shorter in size and yeah, sorry, excuse my bad drawing. Like it becomes tiny, so it's like the potential energy of it, it's decreasing because it's taking up less space. So that's why it happens with energy exchange. A bob of conical pendulum moving uniformly in a circle. So this happens without energy exchange because it's moving uniformly. It's like it doesn't. It's like it's constant. It doesn't change. So it's uniform. If it's uniformly, anything uniformly happens without energy exchange. So a bulb on a vertical spring is swinging up and down. This happens with energy exchange because if it's swinging up, like it's like on a pendulum when you're swinging them up and down, they move from potential energy to kinetic energy back to potential energy. So it happens with energy exchange. And if a man is holding a heavy box above his head, there's no energy exchange because he's not moving or anything. It's just laying there. As long as it's laying there, no energy exchange will happen. So we know now that if it's uniform or if it's just not moving, it's without energy exchange. And if you're changing something about it or if you're swinging it, it's gonna be with energy exchange. Okay, so again, they want to know if it's with or without. A body is changing its speed, but not the direction of its motion. So if it's not changing the direction of its motion, and it's only changing its speed, it's with energy exchange because it's changing its speed. It's accelerating. And if you're accelerating, like let's say you're in a race and you try to run faster, you're putting energy in to run faster, put more energy. So if a body is changing its direction of motion and its speed, this is definitely with energy exchange because not only are you changing the speed like the last question, but also the direction. And a body remains stationary. If it's not moving, there's not going to be any energy exchange. If a body is changing its direction of motion but not its speed. So let's say you have an object going straight, and then it decided instead of me continuing straight, I'm gonna continue left. It's not really changing anything. You're not putting in a lot more energy to go left. So it's like you're just changing the direction. So the same energy it would take you to move straight, you're gonna move straight also, but it's just in a different direction. You're facing another type of straight. So that's why it happens without energy exchange. Next question. To build a fire, ancient people used rocks called fire strikers and small pieces of wood. So like when you see in the movies people rubbing rocks together and creating fire. So let's see how this happens. So when you're bumping them together, it's kinetic energy. Why? Because you're moving the rocks towards each other. So the kinetic energy of the fire strikers moving against each other, they produce a spark. Because if you're putting in enough kinetic energy, you're giving it enough energy to transform into another type of energy, which produces a spark, and it will become warm. Because when there's kinetic energy, it most likely will heat up. Like if you rub your hands together fast, you're gonna feel your hands also warming up. So it supplies them with thermal energy when you rub them together. And now, as the wood burns, its stored chemical energy releases more thermal energy into its surrounding. So we know that wood is like a tree. It's something that used to be living. So we know it had chemical energy. So when you burn it, it's gonna release thermal energy. Like when you make a fire, it's hot, so it's thermal energy. This chapter is mostly like memorization or understanding. You can't know solving really. There is one formula, but it's not seen anywhere in these quizzes. So to charge your mobile phone, you plug it into a socket, supplying it with electrical energy. This one just makes sense because you're not going to give it thermal energy, you're not going to give it elastic, chemical, light, sound. You need to give it electrical energy. So when this energy is given, it has to be stored in a battery. So batteries always store energy as chemical. Like just when you see the word battery, it's most likely chemical. So when your phone rings, the energy is converted into sound because can't you hear your phone ringing? And when you look at it and to see who's calling you, you're gonna see it, and you can't see anything unless there's light. So it's gonna be converted into light energy. Okay, so when the energy changes from one form into another form, we say that it's transformed. And when the energy is given out from one body to another body, we say it's transferred. This one, again, memorization. You can't really find a way against memorizing it. Okay, so for this question, it's asking you to complete the diagram. So, types of energy based on the sensation of hotness. Since it says hotness here, you need to know the different types of heat, because all of these are heat, so that's why you put heat here. So, and now you look, it gives you a warm piece of iron. So if it's a warm piece of iron, it's thermal, because anything to do with temperature is thermal energy. And we know it's random because thermal energy and heat is always random. And infrared, it's like when you're scanning something with an infrared scanner. You can see the different colors of the things and how much heat they give off. So it's radiant energy. And in a hot steam, it's internal energy, because unless you feel the steam or you touch the steam, you're not really gonna feel a much temperature radiating off of it. So it's most likely internal. So if you touch steam, you're gonna feel that it's hot. Okay, so which law of physics states that the energy of the isolated system dilutes itself? This is the second law of thermodynamics. It says that if you have heat in a certain, let's say you have two bodies of water and one's cold and one's hot, and they're connected through a small pipe. So if the hot thing is always gonna try to give off its energy to other things. It's never gonna leave it. It's never gonna keep it for itself. It has to dilute it. So you'll end up finding that it's gonna keep diluting itself until both bodies of water are the same temperature. So that's the second law of thermodynamics. And the most dilute form of energy is random molecular kinetic energy. Just memorize it. Okay, so fusion. Here we have, it's telling you, describe the energy transformation in the sun. So if it gives you one deuterium atom, it's kind of giving you that you need another deuterium ion, because if you even look at it, they look the exact same. And two deuterium ions. I think, if I'm not mistaken, deuterium is isotope of hydrogen. So yeah, if you have let me see, John. Bro, I have a periodic table here, and yeah, deuterium is isotope of hydrogen. So when you have two isotopes of hydrogen, two deuterium atoms, when you're combining them by fusion, because here you could see it's not fission because it's two and making something bigger. So when you combine them by fusion, you're gonna have two protons. And if you have two protons, you know that the entire thing changes. So look at your periodic table and see what element on the periodic table has two protons in it. And when you look, you're gonna see that it's helium. So that's how you put helium, and it also has to give off energy. Because this happens in the sun, and you can feel the heat in the sun, especially like if you live in hot countries. For the example, the UAE, the sun, like you can obviously feel the energy. Okay, so which model of radiant energy explains the ability of light to travel at a constant speed through a vacuum? Okay, so for these questions, they have there's this entire chapter in the book explaining the theories behind it. For that chapter, it's really like I advise you go and read it in the book. It's really like you need to read it, kind of. So at a constant speed through a vacuum, if it's a constant speed, you're gonna think of it as a wave, because it can be particle, like particles can move at a constant speed, but it's easier to think of it as waves moving at a constant speed because they're like connected in some way. The photoelectric effect, like I said again, this is something you have to read from your book. Let's see if I have it like opened in my book here. Yeah, I don't think I have it in my book. The chapter 8, yeah. Here I have a PDF of the book. This you can find it on your SDP. Let me just go down. Yeah, see, here's what I mean by the thermodynamics. If you have a hot body, it's gonna try to keep diluting itself until both of them became the same temperature. So anyways, let's go to the point where we need it. And yeah, here we are. We're getting closer. Yeah, here it is. This chapter, read it out of the book. It's important, and really you can't understand it unless you read it. So here it says wave always travel in the same medium at the same rate. So that's why the first answer was waves. Hala, the photoelectric effect, it's telling you that in a photocell, electrons will come in and they'll knock, light will fall on the surface and knock electrons out. So it's easier to think of it as if it's particles and like they're fighting each other. They're gonna knock one out. So if it's coming in the form of waves, it's like it works, but it's better to think of it as particles. For this chapter, like I said, just read it. So like see here. Wait, is this different? No, it's the same. It's like when you're knocking something out, but you don't want to fully move it. Just when you read the chapter, you're gonna understand it more than if I sit and explain it now. So, photoelectric effect is particle model, and just memorize it. To form interference patterns. This is what this model is explaining, the wave model. So, wait, sorry, this is the book. No, where's the book? And here we go. So, if you have little particles, you're trying to interfere in something. Like, if it's bumping in as in little particles, it's not really gonna affect. But if you're part in a wave is continuous. It has more energy than like little particles. So let's say a person is throwing paper balls at your head. You probably won't even feel it. But if they throw like a soccer ball at your head, you're gonna definitely feel it. So it's the same concept here. Okay, so the principle of the conservation of energy states that in an isolated physical system, it remains constant regardless of the internal interactions of the system. So we know that energy cannot be created nor destroyed. So if you're putting it in an enclosed system, no matter how much it reacts with each other in that closed system, it's gonna have the same energy, because where is it gonna go to? Energy cannot be destroyed, and no energy is gonna come because it can't be created. So in that enclosed system, can it transform into other types of energy? Yes, it maybe could. Could it transfer energy to other things? Maybe also, yes, it could. It's a possibility. But will the amount of energy at the end of it be different than how it was at the start of it? No, it can't be, because it's enclosed. It has nowhere to go. It's trapped. So, as the current flows in an electric circuit, the battery provides energy to the circuit. So, yeah, this one here, it gives you the answer. So, energy is transferred from the battery to the circuit. It told you the answer in the question. So, yeah. For this chapter, like when you're doing the exam, read the questions well, because most of these questions you cannot find your answer unless you read the questions. Okay, so again, for this question, which of the following objects contain chemical potential energy? This is gonna help you find the answer, even if you don't really know anything about this chapter. So, atoms in a random motion. Potential means stuck, potential means not moving. So, this is obviously wrong because it's in motion. Moving electrons, also wrong. You cannot have any motion. Fossil fuels, yes, it has it stored, so it's not moving. Food, yes, this you should know it from like grade 7 science or whatever. Atomic nuclei, no, this one just like it's also explained in the book somewhere. But we know that atomic nuclei do not have chemical potential energy. They just don't. So, yeah. Let's take a minute to answer. Okay, so now which of the following sentences are true? The photoelectric supports the wave nature of light. We said no, it does not, because in the book it said it's the particle. Electromagnetic radiations can propagate in a medium. Yes, they can. And can they do it in a vacuum? Yes, they can propagate almost everywhere. And radiant energy can travel outside of matter. Yes, do you need a box to feel the sun's heat getting into the box? No, you could feel the heat through the air, which is matter, but also like no, it can travel outside of matter. You don't need matter to have radiant energy traveling. And electromagnetic radiation is an example of nuclear energy. No, it's not. It's not an example of nuclear energy. So that's the first quiz fully explained. Now we have the 8.4 to 8.6 quiz. So again, let's start. You have a child moving forward and back on a swing, and when the swing is unoccupied, it has 0 potential energy level. So if the boy is stationary, like as shown in the picture here, he's sitting at the highest point above the ground he can on the swing. What type of energy does this boy have at this time, like now? So of course he has mechanical energy, because we know mechanical energy is the energy when you're transforming from potential to kinetic to potential to kinetic. We're gonna ask how is it potential? It's potential when he's here, you're up in the air, and kinetic while he's swinging. While he's taking the motion, that's kinetic. That's where while he's stuck here, it's gonna be potential. So this constant change between potential and kinetic is called mechanical energy, which is the energy of anything moving practically. And it also has gravitational potential energy, because like we said, it's moving from kinetic to potential, and potential is when it's stuck. And here you can see the boy isn't moving, it's not kinetic. Kinetic is moving. Potential is just sitting. So chemical energy, no, the boy's swing system doesn't. Does the boy inside him have chemical energy? Yes, he does from food. But that's not what the question's asking, so we don't choose it. Kinetic energy, like we said, he's not moving. And elastic potential energy, he doesn't have any tension on him. Like elastic potential energy is like if you have a bow and an arrow. So it's definitely not correct. Okay, so for this question, which of the following objects is the energy converted into mechanical energy? Okay, so for this question, you're gonna have to go to this table that's found in your book and please like memorize it. Okay, it's gonna be hard to memorize it, but this makes up more than half your exam. So if you don't memorize this, like, there's a high chance you won't, like, you get what I mean? It's just memorize, it's really important. I don't know if I can put it in here, like, can I? No. It's fine, I'll just keep going back to that page. So you need to know which energy is converted into mechanical energy. So to use this table, just you have to. So this is what they originally were, and this is what they're transformed into. So you have to see here and mechanical energy. Which ones are mechanical energy? No matter what they started off with, which one they're asking the question, which ones end up as mechanical, which is this. So in your options you have stick of dynamite. So here you just put them down like stick of dynamite, nuclear submarine, electric motor, steam turbine, and gearbox. Electric generator, no, it doesn't. It converts from mechanical energy to electric energy, but it's not converted into mechanical. Stick of dynamite is. Photocell is not. Electric motor is, and steam turbine is. So which of the following objects is the energy converted is initially nuclear energy form? So again, we go back here. Which one is originally nuclear? So we're looking over at this line here. Which one was originally nuclear? We have the breeder reactor, gamma source, and anything with the word nuclear most likely started off nuclear. So we go back. In the nuclear energy form, gamma source, nuclear submarine, it kind of gives it away, and breeder reactor. So, like I said, just memorize it. There's no other way to like get the answers. Okay, so during the burning of coal, we know and we said that coal comes from trees, and trees have chemical energy. It's transformed into thermal energy because it's burning, making a fire, which is thermal. The fission on the sun, nuclear energy, because the sun has nuclear energy and it's transformed into radiant energy, which is the sunlight, the energy you can see. Okay, so for this question, it's asking you which have, you're just gonna arrange them by according to frequencies, this being the highest frequency, this being the lowest. So we know that radio waves are the least, they're weak. IR radiation, which is, I think it's the visible light, like, I'm not sure though, but it's weaker than UV because we know that UV radiation is the third strongest. Gamma is the strongest. Between these two comes X-ray, and so yeah, but anyways, out of the options they gave us, just memorize them. Gamma's always strongest, and in this case radio is weakest. Okay, so for this question, if it's electrons bombarding a metal plate, it's X-rays. Just memorize, because like when you're taking an X-ray of your leg, it's just electrons getting shot out on a metal plate, and where they leave a mark, that's the X-ray. So a warm object, it's infrared, because we said that every object has its own heat, and to test that heat, you need to test the infrared radiation of that object. A radioactive material, it's gamma rays, and a tanning bed has ultraviolet light. Now, next question. So a ball is released from rest, falls on a trampoline, then bounces back to its original height. Assume that the trampoline is located at the gravitational potential energy of 0 level. So it's telling you assume that when the trampoline is unoccupied, it has a 0 potential energy level. So if you have the ball up here, it has, and it's stuck, like let's say you're holding it. What does the ball have? It has gravitational potential energy, right? Because the only thing that's gonna pull it down is gravitation. But that's only if you let it go. So let's say you let it go and now it's moving. And it reaches the trampoline, like here. So it's about to touch the trampoline. See, it didn't touch it yet. So all of this motion here is kinetic because it's moving. It's moving down towards the trampoline. So now when it comes in contact with the trampoline, we know that it's gonna, if it's a bit heavy, it's gonna make the trampoline like dive or like go in. So when it touches the trampoline here, and it's gonna stay for like a few milliseconds. But while it's here, isn't it causing like a tension pulling down? The trampoline is gonna try to want to push it back up. So while it's pulled down, it has elastic potential energy, because like a bow and arrow, when you hold the string and you pull it back, if you release the string, it's not gonna stay back. It's gonna go back, like to where it was originally. So the potential and like the trampoline is the exact same thing. So while it's here, it has elastic potential energy because it's waiting to go back up. So while it's going back up again, it has kinetic energy, and when it reaches back in where it started, again gravitational potential energy. And unless you hold it, it's gonna keep doing this same system until it loses all energy and stops and stays on the trampoline without exerting like a force to pull it down. Next question. Okay, so the sum of kinetic and potential energies of the wrecking ball is its total mechanical energy. Because like I told you, anything moving back and forth from kinetic to potential, from potential to kinetic, back to potential, back to kinetic, back to potential, it's mechanical energy. And this continuous change, it's vibration energy. Vibration energy is a type of mechanical energy. It's when it keeps going back and forth. Like when you pluck a guitar string, it's gonna vibrate, which gives you the sound. In a thermocouple, the thermal energy is into electric energy. Again, you need to see the thermal couple here. And you see it started off as thermal and turned into electrical. Like I said, memorize this table and you'll be good for this part of the exam. In gamma source, we said gamma is nuclear and it's transformed into radiant energy. Again, this is found on the table. Everything here is found on the table. So refer to the table for these answers. So as the car brakes, it's mechanical into thermal, because when you're moving, it's mechanical. And when you brake, it's like it's making friction with the street, so it turns into thermal energy. So in a steam engine, the thermal energy is transformed into mechanical energy, and a microphone sound energy into electric energy, and battery charging electrical energy into chemical energy. All of these, again, they're all found here. Well, other than the microphone. The microphone isn't found here, but it's kind of obvious. When you're talking to a microphone, you're giving it sound, it transforms it into electric, and unless you have a speaker, it's just gonna stay there. Like, it's not gonna be said out loud unless you have a speaker. Okay, so for this question, it's like these energy chains. They're called energy chains. So here they want it for a nuclear power plant. So we need to think of this honestly, logically. You can't memorize it. Well, you can memorize them, but if they bring you a new one in the exam, you can't know the answer. You have to actually read it and think about it logically. So you're gonna start off with kinetic energy of neutrons and nuclear energy in uranium. Logically, this would be the first step, kinetic energy in neutrons, because neutrons, we said they move. And if it's nuclear energy in uranium, the neutrons are moving, so it just makes sense for these to be the first thing. And this, in the end of the power plant, we know that we need to make it into electric energy in wires. It has to be ended with energy in wires, okay? So these will give off radiant energy of gamma rays, nuclear energy, practically. And then it's gonna be turned into the thermal energy of water. Because when this radiation, like, it becomes, like, hits the water or whatever, it becomes thermal energy. Because see here, we know, because it said converted by a water turbine. So we need to know, we know that something has to be to do with water before this. And a rotational kinetic energy of a steam engine. If you have a thermal energy of water and it's getting converted by a water turbine, it's gonna be rotating something, most likely. Turbines rotate. And when it's rotational kinetic energy of a steam engine, it's converted in a generator to turn into electric energy in wires. And like little pro tip, like if you see any arrows pointing down to like a little separate thing, it's most likely wasted heat or wasted energy in general. It doesn't matter what type of energy it is. So again, here we have another question. So again, another chain. Here it's of a water pump. So now we need to think of water. So we have chemical energy in gasoline, and you burn it. When you burn it, it's gonna turn into electric energy in the generator wires, because you're burning it and it turns into electric. And then this electric energy is gonna rotate the generator, because this generator carries water up, because it's a water pump. So, and like I said, if you see anything side thing with coming out of two different things, it's most likely some type of energy loss. So you have the rotational energy of the generator carrying up the water, which is kinetic energy because the water is moving. Like, see, you're lifting the water, and then when it reaches the top, right before it's gonna fall, it has potential energy because it's not moving. Even if it's for a split second, it still has gravitational potential energy. Okay, so this also refer to the graph. This one, really important. So applying brakes, it's mechanical to thermal, burning up a candle, chemical to radiant, turning on light bulb, radiant electrical to radiant energy, and charging a battery of a car, it's electric to chemical energy. For most of these options, like it's common sense. Like if you read them, you're most likely gonna find them out. So like candle, you know that candle has like chemical energy, and you know it has to turn into light energy. And you know that the light bulb also turns into light energy or radiant energy. So just you know that candle is like, if it's natural, like it's most likely chemical, and this needs electrical. You plug it into a wall to turn on the light bulb. And the charging battery of a car, electric into chemical, because you're charging battery, and battery needs chemical, stores chemical. Okay, so for this one, again, memorization, it's the electromagnetic spectrum, and the increasing energy, you're gonna do it. Radio has the weakest, microwaves come next, then infrared, and visible light's always in the middle. Always in the middle, because visible light is what we see. And visible light comes in a rainbow, which ends with violet. So what comes next? Logically, it's gonna be the ultraviolet, then X-rays, then gamma rays. Just memorize this one. All electromagnetic waves travel at the same speed in an empty space. So this one, just memorize, it's common sense. Sorry. So here you have night vision goggles. Like I said, everything releases heat, so if you want to see something in the night, you're gonna have to use infrared radiation to see the amount of heat it's giving off. Food heater, which is a microwave, uses microwaves. Medical imaging, like when you go get an x-ray, uses x-rays, and broadcasting towers are radio waves. And yeah, with that, we're done the quiz, both of the chapter 8 quizzes, and we might make other videos explaining the course revision. Depends on the type of questions in the course revision, of course, and depends on if they're easy or if they need understanding and if they're solving. Anyways, yeah, that's it with the video. Bye.